Igneous rocks classification. As you probably know, all igneous rocks form from the cooling of magma or lava, which is simply magma at the surface. If they all form the same way, then why do all these igneous rocks look so different? And how can you tell them apart? One reason that rocks differ is because the rate at which the magma cooled may differ. If the magma cools deep underground, large crystals can form. If, however, they come to the surface, they'll cool quickly. The crystals will not have sufficient time to grow large, so volcanic rocks have smaller crystals than do rocks formed deep underground. The cooling rate results in one of the most important properties used to distinguish among igneous rocks, the texture. If lava cools quickly, then no crystals have time to form, and the texture is glassy. If it cools quickly, as it would in volcanoes, small crystals can form, and the texture is aphanitic, also known as fine-grained. If, however, the magma cools slowly underground, the crystals that form are large enough to distinguish, and phaneritic, or coarse-grained, rocks form. If, however, the cooling magma has lots of volatiles such as water in it, this would happen at subduction zones, then it can form really large crystals, and the result is a pegmatite texture. Well, let's look at obsidian, a glassy rock with no crystals at all. It's volcanic glass and even breaks the way glass does with conchoidal fracture. Any magma that cools so quickly that no crystals form is obsidian, regardless of the kind of magma. Rhyolite is a good example of an aphanitic rock. Although you might see a speck or two, you really can't distinguish among the different minerals in the rock because they're too small. It's easy, however, to see the different minerals in granite, a common phaneritic rock, which cools deep underground. And here is a granite pegmatite with its huge crystals of quartz, feldspar, mica, and hornblende. These three rocks have different textures and therefore have different names. However, they differ only in their grain size. They have the exact same minerals in them because the magma that produced them was felsic. Fel for feldspar and SiC for silica or quartz. Felsic magma creates rocks with minerals that are not very dense and are usually light in color. Another kind of magma would be mafic, which contains a lot of magnesium and iron. Mafic minerals tend to be dark and more dense. The rock on the left doesn't have any visible crystals. It's basalt, the most common rock of the ocean crust, and it is aphanitic or fine-grained. The rock on the right is gabbro, also mafic, but it cooled slowly, so it is phaneritic. A magma that's neither light nor dark is appropriately called intermediate, and sometimes even andesitic, after the rock on the left, an aphanitic rock formed, as you might guess, in the Andes, which are volcanoes. If, however, this same magma cools deep underground, you have diorite, a phaneritic intermediate rock. There's also ultramafic magma. It produces peridotite. Now, ultramafic magma almost never gets to the surface, so there's no need to learn about aphanitic or glassy ultramafic rocks, just peridotite, which is the main rock of Earth's mantle. Peridotite can be distinguished from gabbro because of the abundance of olivine, a green crystal. I've placed 7 of the most important igneous rocks in this chart. The rows denote texture, while the columns distinguish among mineral content. If this table makes sense to you, then you're well on your way to understanding igneous rocks. But wait, there's more. What if you had a rock with both large and small crystals? That's not right, but it would happen if you had 2 cooling rates. What you would have is called a porphyry. The larger crystals in the porphyry is the result of cooling underground. In this particular porphyry, which is an andesite porphyry, the large crystals are hornblende crystals, these black skinny things. However, most of the rock, called the ground mass or matrix, is made of small crystals, and they are what make this an andesite. This would be an andesite porphyry. Is there such thing as a phaneritic porphyry? Sure, why not? Here we have a granite porphyry. As you can see, most of it is granite, but there's some really big feldspar crystals in there. Look at that huge rectangular potassium feldspar crystal. The feldspar crystal is the phenocryst, while the rest of it is the ground mass. Here's a rock that was part of a lava flow. It's mafic and aphanitic, and it's basalt. The holes are the result of the gases bubbling out of the lava as it cooled, giving it a vesicular texture. Here's some basalt that's so vesicular that it seems to have more holes than rock. At this point, we call it scoria. Scoria could be black, brown, or red. This is the stuff that makes up cinder cones, otherwise known as scoria cones. It cools so quickly that it might even be glassy. Another vesicular glassy rock is pumice. But unlike scoria, pumice is much more likely to be felsic or intermediate. A good way to tell if you have pumice is to see if it floats. Because while pumice floats, scoria doesn't. Both scoria and pumice can be injected into the air by volcanoes. When volcanic ash, cinders, and chunks of rocks are thrown into the air by volcanoes, they land, they weld together to form a rock with a texture that we call pyroclastic. Pyro for fire and clastic for fragments. If the rock is just made of fine-grained ash, we call it tough. But if there are larger fragments in it, we call it tough breccia. Breccia means broken. This is a sample of tough breccia. Sometimes the ash will land when it's so hot that it will remelt, and when it cools, it becomes obsidian. The result is welded tuff, another pyroclastic rock. Here's the final chart that attempts to categorize all of the major igneous rocks. It's by no means complete, but it is a pretty good start. I recommend that you pause the video and take a good look at this chart. When you've made sense of it, you deserve congratulations, for now you can classify igneous rocks. Not bad.